Welcome to Affordable Tutor. Today we are going Master Randomized Complete Block Design, or RCBD. This video will explore a practical framework for controlling experimental variation and increasing statistical precision. Uncontrolled variation compromises experimental precision. RCBD groups units with similar characteristics into homogeneous sets called blocks to control a single source of variation, which the completely randomized design fails to account for. Blocks isolate variation to reveal true treatment effects. The Orthogonal Rule states that blocks are perpendicular to the source of variation. The Variance Rule minimizes variation within the block and maximizes it between blocks. The number of blocks equals the number of replications. To implement RCBD, first classify the experimental units into blocks, then subdivide each block into plots, and finally, randomly and independently assign treatments within each complete block. A block is complete only if every treatment occurs exactly once within it. Operational consistency protects block integrity. Complete all field operations for one block entirely before moving to the next. Also, assign a single researcher to manage all data collection and operations for a single block to isolate human error. The mathematical engine behind RCBD is represented by this model. Yij is the specific yield. Mu is the overall mean effect. Beta underscore I is the block effect. Tau underscore j is the treatment effect, and epsilon underscore ij is the random error. Experimental data is translated into variance matrices to test hypotheses. The ANOVA table includes source of variation, degrees of freedom, sum of squares, mean square, and F ratio for blocks, treatments, and error. Let's look at a case study evaluating nitrogen sources across soil types. The crop is barley, with 6 treatments including a control, blocked across 4 heterogeneous soil types. The methodology uses RCBD with soil type as the blocking factor. Here is the yield data structured by treatment and block. Note the difference between the lowest block total, soil 1, and the highest, soil 3. The grand total is 741.2 kilograms across 24 experimental units. ANOVA reveals highly significant treatment effects with a low p-value. Blocking by soil type was also highly effective, evidenced by the large F ratio of 19.95 and a low coefficient of variation of 5.78%. The analysis shows that ammonium sulfate produced the highest mean yield at 36.33 kilograms/plot. Adding no nitrogen, the control, resulted in the lowest yield at 25.35 kilograms/plot. RCBD is advantageous as it increases precision and is flexible, but it's inefficient if experimental units are already homogeneous or if the number of treatments is too large, reintroducing heterogeneity. RCBD can recover mathematical integrity from a single missing value by using this formula. If 2 or more values are missing, it's better to drop the problematic treatment or block entirely. The statistical value of blocking is quantified by relative efficiency, RE. Our case study showed an RE of 3.472, indicating a 247% increase in efficiency over a completely randomized design. In summary, the RCBD is based on 4 rules: grouping homogeneous units into orthogonal blocks, the linear model equation, independent randomization of treatments, and always checking for a relative efficiency greater than 1. If you have any question, please let us know in the comment section, and don't forget to subscribe to our channel and bell icon for latest updates.